Hello everyone, this is Subramaniam Gantasala. I'm a student at IIT Madras, working under Tiju sir and Prabhu sir. So today I would like to explain you about phononic crystal and how to simulate a phononic crystal band structure in COMSOL Multiphysics. So basically, phononic crystal with a shortcut PNC, it's a acoustic or elastic wave manipulating device, and it can be in 1D, 2D, and 3D depending upon the periodicity. So phononic crystal is generally I would say it's a composite structure of different materials with varying elastic constants, and these materials are arranged in a periodic fashion, like one material is embedded in another host material. So as you can see here, these are the types of phononic crystals. So the 1D, 2D, and 3D depend upon the periodicity of varying of the material. So the name phononic crystal comes in the way such that it uh, it manipulates sound waves or elastic waves, which are the if you go to in the quantum nature. So these are phonons are quantum particles of sound waves, and the crystal comes from the fact that it's periodic and it resembles the atomic or molecular crystalline structure. And basically, so the phonons, as you know, phonon is a quantum of mechanical or vibration energy, and it comes from the condensed matter physics or solid state physics. So the vibrations of an atom about mean position at a particular frequency are termed quantized into something called phonon, which is resembles to a photon, quantum of light. And yeah, so the phonon actually is responsible for these vibrations in atoms, and we can also calculate heat flows and the way a thermal heat flow occurs in atomic structure or crystal structure are calculated using these phononic calculations. Coming to the current application, so phononic crystal, as I explained earlier, is a composite structure of two or more elastic materials, and these materials have contrast in the elastic constants such as density, bulk modulus, and Poisson's ratio, etc. So due to this contrast, uh, there are something called band gaps. Band gaps appear in its band structure. So actually, band structure is nothing but a plot of a phononic crystal, where x-axis is taken as a wave vector and y-axis is taken as frequency. So it's generally a plot of wave vector versus frequency, and it's similar to like band structure in electronic materials or atomic band structures. There it's electronic band structure, but here it's band structure for phonons. And as you can see here, so the band structure is calculated for a unit cell. I mean, in COMSOL multiphysics, we take a unit cell and we apply periodic boundary conditions uh, around the unit cell so that we can get this band structure. So we'll get to the simulation using COMSOL later. And this band structure is taken around the first irreducible Brillouin zone. So irreducible Brillouin zone is the symmetrical part of Brillouin zone, and which is a unit cell of a reciprocal lattice. And this K is a propagation vector or wave vector of these phonons. As you can see, generally in this phononic crystal research, we calculate band structure from gamma x m gamma. So the path might be different, but so around this we have to calculate the band structure. You can calculate from gamma x m gamma, or you can calculate from m gamma x m. It doesn't matter. And the why we calculate band structures, because due to the contrast in the elastic properties, there is something called band gap. So band gap is nothing but uh, region of frequencies where there is a elastic waves or sound waves are forbidden to propagate through the structure. So for example, here we have a phononic crystal with air hole in an aluminum matrix. Uh, so due to the contrast between air and aluminum elastic constants, so we can find a band gap uh, at a certain range from, let's say here, 2.2 to 2.5 hertz. So this 2.5 to 10 power 6 hertz. So this frequency value depends upon the lattice constant. The lattice constant nothing but a periodicity of this unit cell. Yeah. So this is about band structure. Coming to the so another property of a phononic crystal is transmission spectrum. So this document I have shared in the Google Drive so that you guys can go through the steps. For now, let's go through COMSOL Multiphysics and let's see how we can generate band structure for this uh, phononic crystal with basic air holes in a aluminum plate. So yeah, so we'll take this aluminum uh, plate and air holes still drilled in it as a phononic crystal. So let's open. So these are the steps which to follow through COMSOL multiphysics to obtain the band structure. Let me open COMSOL. So COMSOL multiphysics is nothing but a finite element software, so which you can calculate different physical problems like electrical, mechanical, structural, chemical, uh, solid mechanics, which comes under mechanical. So these we can uh, calculate using COMSOL multiphysics. It's a commercially available software, finite element software. So it uses finite element methods to calculate uh, these structural parameters. Let's go through the steps and see if we can calculate the band structure of a phononic crystal as described in the steps through the steps. So first step is to so you can go through a model wizard which takes to the steps uh, to fix a basic set of parameters for a model. So for now, can select you can select any model, 3D or 2D, depending upon the calculations. So let me select a 2D model or 3D model. Let me select a 3D model here. And in this, since we are going into uh, mechanical problems, so should go under structural mechanics and select the solid mechanics physics, add. Next we'll go to study. And the study is basically what we want to study of a solid mechanics problem. So if we want to study like something like band structure, we can go through eigenfrequency studies. And if we want to study transmission spectrum, we can go through frequency domain. So for now I'm selecting eigenfrequency, click done. So this gives a basic interface of a model. So here these are the flow, home, definitions, geometry, materials, physics, mesh study results. So this, so it's a basic simple user interface which goes through all these steps to calculate our required uh, parameters, required model. So let's add few parameters here so uh, that we can continue with this. So I'm selecting a lattice constant as 33 millimeter and radius of the hole I'm selecting as 15 millimeter. The thickness of the phononic crystal plate we can say, so that will be 2 millimeters, and K is 0. So this Kx and Ky. I'll explain you what is K, Kx and Ky. Let me copy and paste these things. So here K is, so we need to, since it's a 2D phononic crystal, we need two parameters Kx and Ky to sweep through the Brillouin, irreducible Brillouin zone, right? And this K, Kx and Ky act as a wave vectors for this band structure plot. And coming to the K, so since we have to calculate through reciprocal lattice gamma x m gamma, so we have to find those with respect to the lattice inverse of lattice constant, and these comes from the reciprocal lattice calculations. And K, we reduce it, we call it as a reduced wave vector, so we give as 0. And Kx and Ky are the parameters which we apply as a periodic boundary conditions. So here we apply Kx and here we apply Ky. So, and in the parametric study, we vary K from 0 to 3, so just so that we can calculate the gamma x m gamma. So gamma to x is 0, x to m is 1, m to gamma is 2. Yeah, so 0, here it's 0, 0 to 1, 1 to 2, 2 to 3. So 0 is gamma and x is 1, and m is 2 and gamma is 3 again. So here we calculate from gamma x m gamma. Since our parameter is done, next we'll go to component. So each component is like a one model, you can say. So first of all, if we want to calculate band structure, we can edit this component parameters and we can calculate. And again, let's say we want to calculate transmission spectrum for a different, it's for a perfect cell or finite cell. So instead of one unit cell, we have to take 10 cross 10 or 5 cross 5 cells. So again, we can add another component from here and we can go through it. Also, we can add some elastic properties of aluminum. Let's say E, underscore AL. So Young's modulus I'm gonna add as 70 GPa, and so density, let's say rho underscore AL as 2700 G per meter cube, and Poisson's ratio, let's say mu underscore AL can, yeah, so we can, this is around 0.33 for aluminum. So these are the parameters required for this. So next we'll go to geometry, and we'll create a model. So since it's a square, so you can go to geometry and choose a block. So here you can choose width as A, depth as D, and height as A. So, and also corner 0, 0, 0. So we can get this block, square block. So height would be D and depth would be A. So this is our phononic crystal unit cell. So x direction, y and z direction. Z direction shows the thickness, and x and y direction shows the phononic crystal. Since we would like to create a hole, so we'll take a cylinder, and the radius is r and height is d, thickness of the phononic crystal. Position will put 0, 0, 0, so that so position we have to put as a by 2 and a by 2, so that it will be center with respect to our square block. Now we would like to remove this. So to create a hole, we can remove this cylinder from this square. So for that we can add difference, and objects to add, click this square block, and object to subtract will click this one. So build all. This is our phononic crystal. We can go to geometry and choose length as mm. Yeah, it's better to view. So our unit cell is ready. Now next thing is to add materials. So here the way to add is we can select, and here we can add material from library, or we can create a blank material with our properties and add for a particular domain. So take a blank material, and the selection is this. Okay, so Young's modulus will put E underscore AL. Poisson ratio will put mu underscore AL. Density will put rho underscore AL. Fine. Now coming to the band structure calculation. So we have to give some periodic boundary conditions, right, to get the band structure. So let us see solid mechanics. Here we can choose any condition to give to the model, and we can obtain results. So for periodic, we'll go to connections, and yeah, periodic condition. So now in periodicity we need to choose Flucket. So this is something called block Flucket periodic conditions. So here it shows Flucket, and we should apply we apply two periodic conditions, one along x-axis and one along y-axis. So let's apply along x-axis, and we'll choose kx and ky. Since our PNC is periodic only in two directions, we can ignore KZ. So we'll just duplicate this guy and we'll clear this and we'll choose in Y direction. So I think our model is ready with respect to conditions and material and geometry. Next step is to do the mesh. So meshing is a very important part, I would say, in these finite element calculations. So depending upon your research problem or the device or the design and material, these and also the application, these meshing things change. So you can have, so basically it gives few options to choose under mesh. So let me choose finer mesh. So it's nothing but the size of element. So 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 finer element is basically, so it divides the whole domain into particular elements and it solves the differential equations basing on conditions over the elements volume or elements area, and then it adds up all the values and it gives it integrates, or it adds up values and gives us value over a surface or line, etc. So for now I'll choose finer mesh. So depending upon this, the number of elements, and let me show you build all. So you see the mesh. So if I choose normal, then number of elements reduce. Let's use finer for now. Yeah. Also you can see how many elements it creates here. So if I put like extremely fine, so it creates 38,000 elements, 7,700, like 45k elements. And if I choose uh, finer, it gives like 1900, 1100, some 2.3k, 2.5k elements. So let me choose finer. Yeah. So now next step is going to study. So here we have eigen frequency study. To calculate a band structure, we have to sweep through parameter k, which is the Brillouin zone parameter, the reduced wave vector. So we'll click here, left click and right click, and we'll find parametric sweep. Here all combinations. Here you can add k. So now here we have to specify the range for k. So we can choose here range, number of values. So start is 0, stop is 3. So gamma x m gamma, so 0 1 2 3. That's the number of values. We need some intermediate values, so it will just create the step size. Let me choose as 40. So we'll do replace. Yeah. So now important thing is to set parameters in eigenfrequency study. So let me choose desired number as 10. So we can choose how many frequencies we want to, how many bands of frequencies we want in a band structure. And since we gave in let me choose kilohertz as a unit. So here you can use these options as it is for now. So let me compute the study and see what happens. So our band structure calculation is completed. So to view the band structure, we have to create a plot. So this mode shape is nothing but eigenmode shapes. So if we want to see the mode shape, let me choose k here 0 and so basically a surface plot, and let me go through wave. So these are the eigenmodes for this phononic crystal in the range of frequencies. Depends upon number of bands we gave, we'll get number of eigenmodes. So let me go through results and create a plot. So it's a 1D plot group. Select 1D plot group and name it as band structure. So we'll choose parameter none here. Uh, Now here we'll choose a global plot. Here we can choose parametric, and in expression we need to give the frequency. So it's a y-axis data, so we need to give the frequency. Go to solid mechanics, global, solid dot frequency, can give in kilohertz. And the axis source data we need to give as outer solutions, and parameter choose expression k. So let me plot. So this is the band structure plot for this crystal, phononic crystal. Let me choose some parameters so that it looks good. Legends are off. So coloring style, set color as blue and choose width. So the frequency we're still getting heads. So let me put kilohertz. Yeah, so actually this phononic crystal has a band gap from more greater than 50. Since we have chosen 15 bands, so we will not reach this whole range, so that we cannot see the band gap. So let me go and change this number of bands in this eigen frequency. Let me put 30, or let me, so let me put 20 bands. Compute. Depending on the number of bands, it might take more time because it has to go through those number of eigen frequency solutions and give us the results. So this study is now completed. Let's go through the plot, band structure plot. So now this band structure, here we can see a minute band gap. Let me go here. So from 56.5 to 62, you can see there is no band here. So it's actually a band gap for this phononic crystal. So this might be small, but it depends upon the design, structure, and what are the materials you have chosen for this phononic crystal. So this is how we calculate band structure. And in the next part, we can learn about transmission spectrum and my project I worked on for my research, MS research, in this phononic crystal area. Thank you.